Hey everybody, welcome back to another video lecture. This time we're looking at amines. So we're going to start introducing nitrogen compounds into the organic structures that we've been naming, that we've been looking at. And we'll look at some reactions as well. So what are amines? Amines are the fourth most common organic molecule because they contain the fourth most common maybe they're not the fourth most common organic molecule. That might not be true. But they contain the fourth most prevalent element, which is nitrogen. So hydrogen, carbon, and oxygen are the three most common elements that we find in organic compounds. But because nitrogen is the fourth most common element that we find in organic compounds, we have a whole class of molecules dedicated to these. And we call these the amines. Now the amines come in primary, secondary, and tertiary form, just like our alcohols did. And all this means is that our nitrogen is either going to be attached directly to a carbon that only has hydrogens on it, or a carbon that has, here it isn't anything like with alcohols. It's actually how many carbons are on the nitrogen. So nitrogen can exist with 3 bonds. We tend to see that in organic compounds. It's going to have 3 bonds. Now there could be a triple bond, it could be a double and a single, but there's going to be 3 covalent bonds and a lone pair of electrons. Now, the simplest, I guess we wouldn't call it an amine, but when we stick all the hydrogens on there, we call this ammonia. So this is ammonia. Now, replacing one of those H's with a carbon gives us our amine, and that's what we have here. So a primary amine has only one of its H's, the nitrogen's H's, replaced with an alkyl group. A secondary amine has 2 of those hydrogens replaced with carbon groups, and a tertiary amine only has carbons on it, no hydrogens. This is going to be important later when we're looking at some of the reactions of amines. So being able to differentiate between the primary, secondary, and tertiary. Now our amines come in a few different flavors. They come in aliphatic amines, which are carbons. They're amines in which the nitrogen is actually bonded to a carbon that is part of a alkyl group. Now, I have an example of that. I guess the first 3 that we're looking at here actually would be just regular, what we call aliphatic amines. Aliphatic. Now, the other kind of amines are aromatic amines, and these are the ones in which the groups, or one or more of the groups that are bonded to the nitrogen are aryl groups. Remember aryl? We'll just call it aromatics. So here you can see there's a benzene on this nitrogen. I don't have another structure to show you of some more of the different kind of aromatic amines, but I guess I could draw one. So we could have, let's say, let's put a benzyl group on here. We can have a phenyl group, maybe a CH3. So again, this would be an aromatic amine because the groups attached to the nitrogen are part of, or have aromatic pieces in them, aromatic benzene derivatives, or they don't have to be 6 carbon rings, but they have some kind of aromatic in them. Now, we can continue talking about the cyclic amines and actually talk about 2 different kinds. Now we can talk about the heterocyclic aliphatic amines and the heterocyclic aromatic amines. And so you can see here the difference is that in the heterocyclic aliphatic amines we don't have any conjugated double bonds. So in some of these we might even get 1 double bond or so, but they are not aromatic in the sense that the double bond is able to freely rotate or move around, as it can here. The double bond can move and move like that. So again, just to kind of note the difference in terminology. Heterocyclic aliphatic has no conjugated double bonds. Heterocyclic aromatic does. Amphetamines. These are, well, amphetamines, methamphetamines, phentermine. These are all similar to the action of epinephrine in your body, which is a type of amphetamine, or like a natural amphetamine. These are amines, and that's why the name is in them. Maybe you're noticing it now. Amphetamine, methamphetamine, right? They're amines. And amines have biological activity in our bodies. Many of them are powerful stimulants of the central nervous system, and a lot of them are habit forming. There's also alkaloids. Alkaloids are basic in that they're not acidic. I don't mean they're just simple. Basic nitrogen-containing compounds, and that kind of comes from the word alkaline too, which means, you know, basic, that has a like high pH. But these are natural products, natural amines made by plants. And they're often found in roots and barks and leaves and berries. In almost all alkaloids, the nitrogen atom is part of a ring, and so it's similar to what we're talking about right now. In fact, caffeine is an alkaloid. Yeah, and actually caffeine isn't made for us. It's made as a deterrent against bugs in plants. It attacks their central nervous system. Let's talk about how we name. So with IUPAC names, we derive the name from the aliphatic amines, just like we did for alcohols. We drop the final E of the parent alkane and replace it with amine. So in this case here, this was a 3-carbon molecule, so a propane. So instead of propane, we'll say propanamine. Where the alcohols, we said propanol, we added the OL. And we'll use a number to locate the amino group on the parent chain. So for propanamine, because we could also do CH3, CH2, CH2, NH2, this would be 1 propanamine. So we need to, again, always use our numbers. If we have multiple amines on the same molecule, then we can call it a diamine, like we said, a diol or a triol with alcohols. And of course, we give the number as well. No need to give a number on a cyclic compound. The amine will be part of will be the number 1. Let's see. Benzene derivatives that have amines get the common name aniline, and alanine is an amino acid. I got them mixed up. Aniline, and this is the simplest aromatic amine. Now, we can name simple derivatives of aniline using numbers to locate the substituents, or if you remember going back to the benzene chapter, we can use ortho, meta, and para. So that's why you see little P's and M's here. Remember, anytime there's 2, we can name them as ortho or para to each other, or just use the numbers. And if there's 3 or more, then we'll have to definitely pick one of these to be the apparent chain, or to use the common name. So we would have to know the name aniline here, rather than calling this, let's say, 1-nitro 4-amino benzene, which we could do that too if we didn't have, as long as somebody could draw it, we could say 1-nitro 4-amino benzene. But if it had a 3rd group on it, we would have to call this aniline. Or if the other group was an alcohol, we could call it phenol, for example. Unsymmetrical secondary and tertiary amines get substituted or get named as N-substituted. N-substituted. Primary amines. So we would take the largest group bonded to the nitrogen as the parent amine. So here we have the choice of this group with the nitrogen, which would be the aniline, or we have the nitrogen with the methyl, which would just be methanamine. And so then we could name this as either N-phenyl, because when you name a benzene as a substituent, it's phenyl, N-phenyl methanamine. But that wouldn't make sense because the methyl is the smaller of the 2 groups. So here, the methyl part gets the name N, like it's on the N, right? Like we would do a number 1, 2, or 3 for any other carbon, and then we call it aniline. Same thing here. This cyclopentanamine is the bigger amine, so that's the parent chain. And then this has 2 methyls on it. The 2 methyls are not on the ring, they're on the N. So we have to say N dimethyl. If there was only 1 methyl, then we would just say N-methyl cyclopentanamine. Okay. Let's see. Do I have any examples that we could do? Let's write IUPAC names for a few other compounds. So let's see. What about something like this? What would the name be? Well, actually, that's funny. I think I just drew this guy, but backwards. Sec-butylamine. So here we're just looking at some common names. And actually common names for amines are really nice because you can just say the groups that are on the amine and then the word amine. So for example, in this guy, it's an ethyl and an ethyl, so we can just say diethyl. Actually, there's a methyl as well. Diethyl methyl amine. Here's another one. So these are all ethyls. So this is triethyl amine. Actually, like common names. Common names are pretty good. I was looking in your book to see if we could name some of these structures, but the only structures they're giving me are, they want us to try and specify the configuration of the stereocenter, which is a good thing to do since we just looked at that in the last chapter. So why don't we try that? So here, right, we can pretend the hydrogen is in the back there, and let's just make, I guess first we would see if there is a stereocenter. There is a stereocenter in this one, and it's right there, right? This carbon has 4 different groups on it. But what they don't give us is the real orientation. Like it's hard to know if the hydrogen is really sticking forward or backwards here. They don't give us any indication of that. So we can just throw one back there and see if we can figure it out. So with the hydrogen in the back, you remember it's the molar mass that determines which one is the first priority. The atomic number, sorry, the bigger the element. So from carbon, we're going to go 3 directions and see who gets priority. So we got carbon, carbon, nitrogen. So that's going to be priority 1. And then after we've got to our carbons, we'll go out again. This carbon here only has H's on it, and this carbon has another carbon on it. So this is going to be our number 2, number 3. 1, 2, 3 in a clockwise motion would be R. So this would be R configuration. Sorry, that's what your book was suggesting that we do at this point. But we can move on with the naming. So I just showed you some common name stuff. So we can. Oh, actually, let me show you one more common name. So this looks complicated, but if we use the common name, which means we just name all the different groups and say amine, we see that there's just a methyl on here, there's an isopropyl, and there's a benzyl. Benzyl includes this carbon and the aromatic ring. So this is in alphabetical order, benzyl isopropyl methylamine, just like that. All right, let's talk about amine salts. So when 4 atoms or groups of atoms are bonded to a nitrogen, as an example, we could look at this. Actually, I already have it here. My bad. We can look at this guy. It's not drawn out. Let me show you the structure. So we've got NH, CH3, CH2, And, oh, and three, there's three of those, so CH2. We get a positive charge on the nitrogen. And so it gets associated with an anion, in this case a chloride ion, and it's a salt. It becomes a salt. Now, to name a compound as a salt of the corresponding amine is we replace the ending amine, or if it's aniline or pyridine or pyrimidine, we change it we change the amine into ammonium, and that has to do with the fact that ammonia is NH3 and ammonium is NH4 plus. So the name comes from that nitrogen compound. So amine becomes ammonium, or aniline becomes anilinium, or pyridine becomes pyridinium, pyrimidinium, okay? We would change it in that sense. And then we add the name of the anion. We say chloride. So let me give you a couple more. Let's take so this guy right here is dimethylamine, or we could even call it N-methyl methanamine. This thing is a base. These amines are bases, and so they grab hydrogens with their lone pair from water or from acids. And so these will react with acid to form salts, and they will also react with water to form, well, to become kind of charged and to be more soluble in water. So let's show what happens when this thing reacts with, let's say, an acid like HBr. So it's going to, acids like to lose their stuff. That's what happens. And this nitrogen wants to gain it. So we're going to form a bond to hydrogen. That's going to make this positively charged, okay? And it's going to associate now with this bromine. So the new name would be dimethylammonium bromide. Or this one would be N-methyl methanamonium bromide. N-methyl methanamonium bromide. Dimethyl ammonium bromide. Amine becomes ammonium. Methanamine becomes methanamonium. This happens anytime it gains that charge. Let's talk about some physical properties. So like ammonia, low molecular weight amines have a very sharp penetrating odor. So triethylamine, for example, is the smell associated with decaying and rotting fish. There's two other particularly stinky amines. 1,4-butane diamine, we call this putrescine, and 1,5-pentane diamine, we call it cadaverine. And you can use your imagination on why we call it those things. Amines are typically even, what was I going to say? Oh, I was going to go back to this triethylamine. So with triethylamine, even in cooked fish or, a fishy meal that you're eating, it can have a kind of smell to it. And so what you can do to neutralize that is add lemon juice. Lemon juice is acidic, and it provides a hydrogen ion to those compounds, turning that triethylamine into triethylammonium, which doesn't have a fishy smell. No smell, smell. So that's an interesting thing to find out why, that might have been the reason people liked using acidic to pair with their sort of seafood. One of the other things about ammonia or amines is that they are able to hydrogen bond. amines are polar, and they have NH bonds. Being polar means that you can dissolve in water pretty well. They're polar because they have that lone pair of electrons on top of the nitrogen that sort of draws or makes the overall molecule, have an overall negative side and a sort of positive side underneath the nitrogen. So that already makes them stick together. That increases the boiling point of amines. And then we also have the hydrogen bonding. The nitrogen has a lone pair to be an acceptor, so it can bond other amines. But then, depending on how many hydrogens it still has, so a primary amine would have 3 hydrogens or 2 hydrogens here. Yeah, a primary amine would have 2 hydrogens, so this would still be an R group. I'm sorry. That would be this R group here would be an H. And so then other nitrogens could still potentially hydrogen bond with those. So these have high boiling points. What's good to note is that tertiary amines cannot hydrogen bond to each other because none of them have H's. So even though tertiary amines could hydrogen bond with water and still be soluble, we'll see that in terms of boiling point, from high to low, it's going to be primary, secondary, and tertiary, because these guys do not have hydrogen bonding ability. All right, so unable to hydrogen bond. You can see that they don't have any hydrogens to bond to. All right. Again, in water, though, these things are pretty soluble because this nitrogen can hydrogen bond to the hydrogens on water molecules. Just to show you what some of these bonds look like. Now, or what some of these physical properties look like when we compare an alkane to the amine to the alcohol of similar molecular weights. So the alkane, of course, only dispersion forces, London dispersion forces, keeping those held together and in liquid form. So they boil at -88. Amines have, as I mentioned, the ability to hydrogen bond with each other with the exception of tertiary. So this one right here shown is a primary amine. So -6 degrees, and then the alcohol, similar molecular weight, 65. So what this tells us is that the NH-N hydrogen bond is actually weaker than the OH-O hydrogen bond. And this has to do with the difference in electronegativity between N and H. It's only 0.9. Where for oxygen and hydrogen, it's 1.4. So there's a much bigger difference in electronegativity. So we see a much bigger sort of dipole and a bigger hydrogen bond effect. All right. Now, I mentioned that all classes of amines are going to form hydrogen bonds with water and are more soluble in water than hydrocarbons. So we can add amines to the soluble hydrocarbon, or to the soluble organic compound list, like we have with our alcohols. Most of the low molecular weight amines are completely soluble. Higher molecular weight amines are only moderately soluble, and we can basically say if there's 5 carbons or more, they tend to be less and less soluble. Unless you stick more and more amines on them. If it was a diamine or a triamine, then it would actually be more soluble again. So I mentioned earlier that ammonia is a weak base, and in aqueous solution, it'll actually pull off a hydrogen from the water molecules. And so this is what makes it soluble in water, and also what adds to its basicity, what makes it turn the pH or raise the pH up when it dissolves in water. And that has to do with the leftovers of the water being a hydroxide, and this is the base molecule. So in the acid-base reaction between the amine and water, it does involve a transfer of a proton. We've seen that that's a pretty good catalyst sometimes in organic reactions to have proton transfer. And so you'll see amines are pretty good at doing that and are also pretty chemically active. Now I've got the base dissociation constant here to show you for what this reaction with water looks like. What we do with this is, in this case, they're taking an amine, they're taking CH3 NH2, and they're showing that when you add it to water, it's going to produce CH3 NH3 plus and an OH minus. And then what we do is we set up something called a mass action equation. We take the products, or the concentrations of those products, once this thing hits equilibrium. There's a forward and backwards reaction happening here. Once it stabilizes, we see how much of each is present in solution. Now, strong acids, they make so much of the top stuff, and there's so little of the remainder that this fraction, right, this is just a fraction, is really, really big. It's like so much bigger than 1. When we see a small number, so 4 10 to the minus 4, that implies that there's actually a pretty significant amount of this stuff left over. So this isn't all gone. It didn't completely dissociate. And that means it's not a strong base. Strong bases will completely react. This did not do that. It stays primarily in this form, but some of the molecules are able to go this way and act like a base and pull off a hydrogen. And we use this setup here to calculate something called a Kb. And we also use this pKb to help measure base strengths. And usually, I think the way it works is sort of inverse. The lower the number, the stronger the base. The higher the number, the weaker the base. I might have that backwards. Let me see if I can find that out here. Okay, yeah, I have it right here. Boom. So you can see as the number gets smaller, there are stronger bases, and bigger numbers are weaker bases. So just going back here real quick, this one here with a pKb of about 3.36 is pretty strong for a base. And just to point out, aliphatic amines, which are what we're looking at here, have roughly about the same base strength and are slightly stronger bases actually than ammonia itself, NH3. This is an unencumbered molecule, doesn't have any carbon groups on it. This thing still reacts with water, just like we've been looking at, to form NH4 plus and OH. And what we're saying here is that the aliphatic amines are actually slightly better at doing this than ammonia. Now, our aromatic and heterocyclic amines are considerably weaker bases than the aliphatic ones. And while comparing aliphatic amines are weak bases by comparison to inorganic bases. So just though we're saying aliphatic are stronger bases than these aromatics, if this thing went all the way up to actual strong bases like NaOH, you would see that this guy's actually not very strong of a base at all, which is relatively speaking between aromatics, ammonia, and aliphatics. The aliphatics are pretty strong. Okay. Continuing talking about the basicity of amines. So given that the basicity of amines, or the basicities, we can determine which form of an amine actually exists in body fluids, let's say like blood. So in a normal healthy person, the pH of blood is approximately 7.4, which is slightly basic. And so if there was an aliphatic amine that's dissolved in blood, it is predominantly in its protonated form. And so let me, I guess I can show you an example here. So here is dopamine, and here is dopamine in its protonated form. Now, it would take a really high pH to remove the extra hydrogen that's here. So most of the biologically active amines and even amino acids that we'll look at later in these chapters are going to have positive charges on their amino groups, because the the pH would have to be really high, meaning that because pH is a reflection of how much, let's say this is 1 and this is 14, it's a reflection of how much hydrogen ion there is. And there's a lot at pH of 1 and like none at pH 14. And it switches. There's hydroxide ion that's super present at high pH and then isn't at low pH. When hydroxide is present enough at high pH, that OH pulls one of these extra H's off and deprotonates an amine. So this is what we're saying, and we're not going to get into the well, we'll talk about it with amino acids, and it'll come back. We will be able to actually calculate, and I'll show you how to tell what charge an amino is going to have, but it all depends on the particular compound. But in general, in our bodies, most of the amines are present as protonated forms, meaning they're in their salt forms, or as their ammonium forms. Okay. Assume that an amine, like this guy, so this is a primary amine, has a pKb of 3.5, and it's dissolved in blood that has a pH of 7.4. So the pKb is 3.5. So that's a measure of sort of how good of a base it's going to be. We first would write the base dissociation constant for the amine, and then we would solve for the ratio of the protonated form to the non-protonated form. So we would write out this equation, we would get our pKb, and then we would solve for the ratio of the protonated to unprotonated form, meaning we would just, divide by hydroxyl, or the hydroxide concentration. So then substituting the values for Kb and hydroxide would actually give us a ratio. So we know these numbers, and we would know the hydroxide or the hydroxide ion concentration. We'd be able to get this number. We could actually calculate how much more, right? Because this is a ratio. This is a giant number. If these were in equal amounts, this number would be 1. So we can actually see how much more of the protonated form we would have than the non-protonated form. It matters here that the pH was 7.4 because we could use that to find the pOH, which is the concentration of hydroxide ion. In this case, it would be 6.6. And then all we have to do is 10 to the minus 6.6 to actually get the concentration of hydroxide. So that's where this number comes from. pKb, same thing. We just take 10 to the negative 3.5, and we would get the Kb. There's a few rules that we're not really looking at here. When you're calculating pH or pOH, I'll just tell them to you. You take the negative log of the OH or of the H, and you just get to put a P in front of it. So negative log of OH is pOH. Negative log of H is pH. Negative log of Kb is pKb. To get out of that, you take 10 and you raise it to the negative, let's say, pH, and that'll give you back just your hydrogen ion. Or 10 to the negative pOH will give you back your hydroxide ion concentrations. Anyways, this can be used to show how much or in what form was going to predominate. Again, we could substitute these numbers with, we could go and plug in a different value for pOH, maybe one that's really high, right? Like I was saying earlier, we would have to have a really high pH in order to have a predominantly unprotonated form. And you can imagine that that's already going to happen, right? If we make this number, if we make this concentration bigger, it's just going to make this number smaller. Anyways, this isn't math that you have to worry about. This is something your book thinks is useful. Reactions of amines. The most important chemical property of amines is their basicity. Amines, whether they're soluble or insoluble in water, will react quantitatively with strong acids to form water-soluble salts. So we can react them with acids and make salts out of them. That's the best thing we can use amines for. And again, this is important. We store lots of the biologically important medicines and such as their salts. And you can even see here, norepinephrine is actually only slightly soluble in water. So that wouldn't make it very good at being, a chemical messenger in your blood. But the fact that in our slightly, I guess 7.6 is slightly basic. But for amines, this means they're mostly protonated, and you have a pH, you have a bicarbonate system in your blood, which is slightly acidic, slightly basic. It's a buffer. So not necessarily HCl specifically, but this would be the form that would exist in your blood. It would be norepinephrine hydrochloride, or norepinephrine, norepinephrine hydrochloride. I wanted to say the ammonium name. I don't have the ammonium name. I don't know if we have chloride ions actually floating around in our blood. I'd have to look into that to see if we actually counter ion with chloride, or if we counter it with the bicarbonate. I think we counter with bicarbonate. So let's do some examples. So here we have some amines, and we're just going to react them. So here, this is a secondary amine, right? And if you wanted to show that, this is a nitrogen with a CH2, CH3, CH2, CH3, and a hydrogen. This is going to react with HCl to gain that hydrogen. Remember, there's a lone pair on that nitrogen. So now it has, not what I wanted. Now it has two hydrogens, a plus charge, and a Cl minus attached to it. Well, not attached to it, but associated with it. You could also just show that as CH3, CH2, 2, NH, 2 plus. Like that, Cl minus. This guy, all right, tricky. They're trying to see what we're going to do with this. So in this case, they want us to name them also. Name the salt. So this was diethyl amine, if we use common name. If you don't want to use common name, this is N-ethyl ethanamine. And so this would be diethyl ammonium chloride, or N-ethyl ethynammonium chloride. All right. What do we have here? We have pyridine. So this is pyridine, P, Y, pyridine. Now, I wouldn't typically consider this to be reactive. That's odd. Oh, my bad. Reactive, no. Basic, yes. So there is a difference between the reactions of amines and the fact that they're basic. Okay? Technically, everything's a reaction. So the fact that they react with water and acids, right, is a reaction. But those are their base, because water is an acid and acids are acids. So it being a base always happens. Now, what doesn't always happen is the reactions. And the reactions sometimes depend on whether you're primary, secondary, or tertiary. So I was thinking about that right now, wondering if this tertiary amine was going to react. It is, because we're talking about the base. So it is going to grab a hydrogen off of whoever's throwing hydrogens out, and this acetic acid right here is throwing out hydrogens. So we're going to get this pyridine, like that. with a hydrogen on it. And we're going to get left over. This was acetic acid, so this is now acetate. Don't worry, you don't know how to name those yet. Oh wait, did we do carboxylic acids? I think we did. So maybe you do know how to name them. Unless we didn't, and then you don't. I feel like we just did alcohols. Yeah, we didn't do carboxylic acids. Alcohols and amines, then we'll do, or we did aldehydes and ketones, but carboxylic acids are yet to come. Okay, so that's acetate. So this would be pyridinium acetate. Again, all amines are basic, whether they're primary, secondary, or tertiary. Let's see. What else can I say? So as long as you guys know your primary, secondary, tertiary, you know the difference between aliphatic, aromatic, or heterocyclic, know how to name some regular amines using the IUPAC system, know how to name some of the simple common ones, know the aniline benzene derivative, know about the physical properties, how they compare to other amines, how the amines compare to each other in terms of boiling point, and then how they compare to in terms of other organic compounds in terms of boiling point, and how they fare in water in terms of solubility, and then be able to describe their basicity in terms of a reaction like this. So I might give you, this shown, and your test question might be, tell me the name of the product. Do you know what I mean? You're going to pick the name. So be able to at least know how to go from an amine to their ammonium ion name, but it would help if you could draw it also. Characteristic reactions of amines. Remember, all amines, whether soluble or insoluble, will react with acids to form salts. And that's actually something we use in lab. We can actually use this property to separate the water-soluble amines from the non-water soluble ones. Okay, all right guys, well, I will see you in the next video. Take care.